Okay. Thanks, Terry. Okay, so as I told you before, how to determine the number of section and where we're supposed to cut in the in one beam like that is whether the section can represent one continuous part. Okay, a section only can represent one continuous part. So, for example, from A to P, there is no force, so it continues. It can be represented by one section. From P to 2P, it's continuous. There is no force, no moment. It can be represented by one section only. The same for the last one, from 2P to P. Okay, but the problem appears if there is a distributed force. Okay, if there is a distributed force, as long as the distributed force continues, for example, like this, is a continuous distributed force because it's just a triangle going up like that. Okay, that one is still can be considered as a continuous region. So a continuous region can consist of a continuous distributed force. Okay, but if the distributed force is not continuous, okay, for example, it's going like this, because here there is a sudden change of distributed force. At the beginning, it's going up, then after that, it's going down. So at that particular part, it's not continuous. Because of that, the region from A to B, where originally we can represent only with one section, now we have to represent it with two sections. Okay, here and here, for example. Okay, so that's how we determine on the number of section. Okay, but for this particular problem, it's actually simpler than that because there is no distributed force. Okay, only considered force at P and 2P there. Okay, at the beginning, as I told Irsyad Nabil just now, of course we have to start with solving for the external forces. Okay, solving for the external forces. Okay, Irsyad Nabil, at A, what we have at A? It's a pin.
AX and AY.
Correct.
Yes.
How about AB? It's a roller.
BY.
BY. Okay. There are three unknowns, and we have three equations as well. Okay. Using sigma fx equal to 0, what will we have here, Nabil?
Yeah, AX is equal to 0.
That's correct. Okay. Then I want to use sigma moment at A equal to 0 to find for By. What will we have for the equation here, Nabil?
P times L over 4 minus P 2P times
2P, 2P times
2P 3 over 4.
3 over 4, right?
Yeah,
3L over 4. Okay. What else?
Times Py
plus Y
L times L
equal to 0. From here we got By, right? What is the value of By here in terms of P? Six PL per 4 minus PL per 4. So 5PL per 4 divided by L. So 5, right? P per 4. Correct or not?
Yes, I think so.
It's supposed to be correct. Okay. And after that, using sigma Fy equal to 0. we will have what we have here.
P
AY
plus P
P
minus 2P plus 5P over 4.
Okay, 5P over 4. So in this case, AY will be, what is the value of AY there?
1 over 4P.
Sorry?
P over 4.
P over 4. So P, yeah, correct. Okay. P over 4, positive or negative here? This one is P minus P. Oh yeah, wait. This one is minus P become positive P. Oh, it's supposed to be minus, right? Yeah, negative P over 4. Okay, so now we know all the forces which is happening there. So now it becomes like this. The forces there becomes like this. We have P over 4 negative, so it's supposed to be going down, right? P over 4. And we have 5P over 4 here. And then at L over 4, we have P going up. Then here we have 2P going down. So this is our last free body diagram, right? Correct, right? Irsyad Nabil?
Yes.
Okay. And as we talked before, we will have a 3 section. This is number 1, number 2, and number 3. Okay. Our first section will walk for x between 0 to L over 4. Correct, right?
Yes.
Yeah. Okay. Now let's draw the free body diagram of the first section. Okay, what we have there in the first section.
We have P over 4.
Yeah, P over 4. What else?
M.
Normal force, is it necessary or not?
No, I don't think so.
Yeah. So it's not necessary to draw the normal force. Okay. What else?
Yes. Shear force.
Going up or down for positive sign?
Up.
Up, are you sure? Remember, right? The sign convention is supposed to give the clockwise rotation to the beam, right?
Oh, okay, down then.
Yeah, it's supposed to be going down. V. What else? How about moment?
Also down.
Moment down. Clockwise or counterclockwise?
Or counterclockwise for moment.
It's supposed to be counterclockwise because for moment, positive is supposed to give a smiling deformation, right? Irsyad Nabil?
Oh, yes.
Yeah, remember what that, okay? For positive sign of the moment, it's supposed to be like this. Okay, on the right, it's supposed to be like counterclockwise. On the left, it's supposed to be clockwise. Why? In order to create the smiling deformation on the beam. Okay. Then, what we have here then. In order to solve for phi and m, okay, we will solve for phi first. For phi, we will use sigma fy equal to 0. Okay, in this case, what we will have here?
P over 4 plus V.
Yeah, P over 4 plus phi equal to 0. So phi is equal to minus P over 4, right?
Yes.
Okay. How about moment? We will use sigma moment at A equal to 0.
Just M, right?
No, not just M, because P over 4 is with P0, but we have phi, right?
Oh, V is also included. Okay.
Yeah. So phi there, we're supposed to add it there, right? So for phi here, we have to multiply it with X, right?
Yes.
So it's minus or positive? Positive or minus? Plus or minus?
Minus.
Minus, you sure? Minus?
Wait,
Because
positive. Yeah.
phi is going downwards, right? Moment is positive. It's counterclockwise. So counterclockwise is positive. Phi will give a clockwise moment. It's supposed to be negative. But remember, the value of P, if Phi is negative, right?
Negative.
Yeah. So
we
at
can
the
use
end, it will
positive.
be positive, correct? P over 4 multiplied by X equal to 0. So we will get that M is equal to
XP over 4. Negative XP over 4.
minus PX.
IPX.
Yeah. That's our first. Okay. That's our first cut. Okay. For the second cut, yeah. For the second cut, it's supposed to work for X between L per 4 until X. What is the X there? Is supposed to be 3L per 4, right? Okay. And the free body diagram, it's supposed to be like this. What we have there, P over 4 still there, right? And then we have P here. Sorry. Yeah, we have P here, and then we have the section. Okay, like this, right? Yes, Nabil?
Yes.
And then we supposed to give the shear force and moment as well, because the side is the same, so the positive direction is the same, right? Okay, Shad?
Yes, sir.
As usual, we can solve for the phi using sigma Fy equal to 0. Okay, in this case, what we will get, Irshad?
P4. Wait, negative P4 plus P minus V.
Okay, plus P minus phi equal to 0. So phi is supposed to be phi P over 4, right?
Oh, yeah.
Okay, and lastly, we're supposed to use the sigma moment. The distance here is X, but the distance here is L per 4. Okay, using sigma moment equal to 0 at A, what will we get?
P times L4, L over 4.
Okay, P times L per 4, counterclockwise positive. Then what else?
Minus V times L over 4.
No.
V times X, sorry.
Yeah, phi times X. And we know the value of phi, right? 3P over 4.
3P over 4.
So it's 3P over 4 times X. Okay. And then how about the moment? M there plus M, right?
Oh, yes.
Equal to
Counterclockwise.
0. So the equation will become M is equal to we cannot join it together. So this one is 3px over 4 minus pl over 4, like this. Okay.
Yes.
Last one is for the section between 3L over 4 till L. And the free body diagram there is supposed to be like this. Slightly longer. We have PL over 4 we have P, and we have 2P, and as usual, because the site is still the same, phi and moment. Okay. Correct, right, Nabil?
Yes.
But at the same time, this one it's becoming more complicated. So there is other way to do the third section. The third section, we can choose to do the right side, right, instead of the left side. Okay, if we do the right side, it will be just like this. Okay, still third section. Okay, still the third section. If we do the right side, it will become like this: 5p over 4. That's it. Do you get it? Yes, yeah. But remember, the phi there, the positive sign is supposed to be going up because it's left side right now. So remember, for phi, the positive sign is supposed to be giving a clockwise direction, and moment is supposed to be giving like this. Now it's become clockwise because it will give you a smiling face. Okay, so this one will give the same results as this one. But remember, if before, okay, if before from the left edge to the cut, we have X there, okay, now here, the length from here to here becoming what? Can anyone tell me what's the length here? How about you, Irshad? What do you think? The length there for the shorter cut here is supposed to be what?
We can't use X anymore.
We can actually, but remember X is from the left, right?
Oh.
And the whole length of the beam is L. So if we use it from the right, what is
minus
the
X?
Yes, correct. L minus X. Now what we have here is L minus X. Correct. Yes, yeah. So now our length is not X anymore, but L minus X, because we use from the right cut. We use the right cut instead of the left cut. Okay. Now, because it's much simpler, I will just do the calculation for this one. Okay. Using sigma Fy equal to 0, we can find for phi. What we have there, Irshad?
Phi is negative 5p over 4.
Okay, phi is equal to minus p over 4. Okay, and using sigma moment at p equal to 0, what will we have there?
5p over 4 times L minus X.
Okay, 5p over 4 times L minus X. Okay,
minus M.
Minus M, correct. Okay, why minus? Because phi here is actually giving, if we use a sigma moment at p is here. Okay, if we use a sigma moment at p, phi supposed to give a clockwise moment, the same as M, but remember the value of phi there is minus. So minus multiplied by minus multiplied by minus there is supposed to be plus. Okay, equal to 0. So M equal to 5pl over 4 minus 5px over 4. Something like that. So this is the equation. All of the equation for phi and moment for those three regions. Okay, this one and this one is for first region. This one and this one is for the second region. This one and this one is for the third region. The next thing that you're supposed to do is to draw, to draw the what you call it, the diagram. Okay, but remember now we already have the equation. Okay, so it will be simple for us to draw the diagram. Okay, we have we have P over 4. We have 5P over 4 and P to P. Okay, this one is P, this one is 2P. Okay, for the phi, for the shear force, the first section, the value of the phi is P over 4. Okay, minus phi over 4. So it's supposed to be like this. Minus phi over 4 minus 5P over 4 and 3P over 4. Okay. Okay, the first section is minus P over 4. So let's draw it. It's supposed to be this one. Minus P over 4. Then after that, the second section, it's 3P over 4, positive. So roughly here, 3P over 4, positive. And the last section is minus 5P over 4, roughly here. Okay, so this is your shear force diagram. Okay, this one is minus P over 4. This one is 3P over 4, and this one is minus 5P over 4. Okay, that's your shear force diagram. Now let's go for the moment. Okay, for the moment we start with this one for the first section, and then this one for the second section, and then this one for the last one. Okay, in order to make it simpler, because you can see, right, this one is linear, it's linear, and it's linear. So in order to draw for the linear curve, it will be simpler for us to know the original one, the starting point and the end point. Okay, the starting point for this one is x equal to 0. So for the moment for x equal to 0 is what, Irsyad?
0.
0. Just put 0 here, okay? And then the endpoint is x equal to L per 4. Okay, the moment at x equal to L per 4 is what? Supposed to be
Minus P over 8.
Yeah. Okay. No, 16.
16.
Right?
Yes.
Minus PL over 16. So that's our starting point and end point for the first region. Now, for the second region, the starting point is supposed to be moment at x equal to the moment at x equal to L per 4. Okay, what is the value of the moment at the x equal to L per 4 here?
3PL over 16 minus PL over 4.
supposed to be p minus 4pl over 16, right? So
yes.
it's the same as this one, right? Minus pl over 16, right?
Yes.
Yeah. Now we want to get for the endpoint x equal to 3l per 4. What is the value of moment there?
Is the endpoint not L over 2?
L over 2? No, no, no.
Oh, no?
This one, right? This one, this one
Oh,
is
yeah,
L
yeah.
over 4, and this one is L over 2.
L over
So,
2
but the x will become, sorry, this one is L
from
over 2.
origin.
Yeah, the x is from the origin, so we will have a 3L per 4, right?
Yes.
Oh.
Sorry.
Okay, and what we will get? 9pl over 16 minus 4pl over 16. So supposed to be
5pl over 16.
L over 16 positive. That's the endpoint. Now we go here for the third region. That the starting point is x equal to L 3L per 4. Yeah, 3L per 4. That's the starting point. The value there is supposed to be what?
5pl over 4 minus 15pl over 16.
So it's 20, right? 20pl
20.
over 4 minus 15 pl over 16. Okay. Yeah, so it's supposed to be the same as this, right? 5pl over 16, right?
Oh, yes.
And the endpoint
L.
supposed to be 0, right?
Yeah.
So now we know all the value for the moment. So we can use the starting point and the endpoint to draw for the diagram. Okay. When x equal to 0, the value, okay, wait a minute. So it's minus, going positive 5pl over 4 and going 0. Okay. So now it become like this. This one is our M. Yeah. Yep, like that. So from the beginning, it's supposed to be 0. Then after that, it's supposed to go to the minus PL over 16. Then after that, it's supposed to be going to the 5PL over 16. Then after that, it's supposed to be going to 0. So roughly, it's supposed to be, this is the graph that you will have. Linear, linear, and this one is linear as well. This one is minus PL over 16. This one is 5 PL over 16. Okay. When you draw in your homework, please use a ruler. Okay. So this is our diagram. You get it, Irsyad Nabil?
Yes, sir.
Oh. We do the calculation before as well, and it's the same. The result is the same. Okay. But the idea is like that. Okay. The idea is like that. For this particular problem, anyone want to ask question, please? Before we go for the next problem. Anyone? Davi Rizky. Hello, Davi. Davi Rizky, are you there? Aryoga Pramadipa, are you there?
Yes, sir.
Okay, do you understand?
Yeah, more or less.
Okay, good. If any of you have any problem with this, please let me know, okay? Okay, now I think we will this one will become our last exercise for today. Okay. Zafran. Hello, Zafran.
Yes, sir.
Okay, Zafran. Please help me to finish this one, Zafran. Okay. First, what do you think? How many sections that we have to do in this particular problem, Zafran?
I think first we have to solve the distributed force.
Yep, correct. We actually have to solve here the external force there. But before that, I want to know whether you understand the number of sections that we have to put here. How many sections that we have to use here?
I think we will have to.
2, correct. Yeah, from 2 kilonewton until the starting point of the distributed force. Yeah, we need one section. This is the first section, and then from the starting point of the distributed force until the end, we will have another section. Okay, so the first section will represent this part. The second section will represent this part. Yeah, the first section between the concentrated force 2 kilonewton and the starting point of the distributed force, there is no force and moment at all. So it must be continuous there. And the second region is start from the starting point of the distributed force here until the end point of the distributed force. Okay, remember, I told you before that if we have a distributed force, as long as the distributed force is continuous, okay, that particular region will be continuous as well. This distributed force is continuous because it's constant, right? So it can one section is enough to represent that particular region. Okay, but as Zafran said, we have to start with the finding the external forces at B first. Okay, finding the external forces at B. So the free body diagram will be here, 2 kilonewton. Okay, and we have a distributed force here. Oh yeah, 1.5 kilonewton meter. 1.5 kilonewton per meter. And at B there must be what forces that we have at B, Zafran?
By.
By, what else?
And bx.
Bx. This one is a fixed. This one is a fixed joint. Okay, for fixed joint, it will give you the horizontal force, vertical force. Okay, but at the same time, it will give you moment as well, Zafran.
Okay.
Okay, because when we talk about fixed joint, right, cantilever like that, it's like you clamp it. You clamp. You did a clamping on that particular thing. So even though it can give a moment at this particular joint. Okay, Zafran?
Okay. Okay.
So please, for all of you, if you face this kind of joint, okay, this is all the forces that you're supposed to give, okay, not just horizontal and vertical force like a pin joint, but you have to add a moment as well, okay. But in order to solve this, because as I told you before, we are solving for the external force, right? What we supposed to do with the concentrated force, distributed force 1.5 kilonewton per millimeter.
1.5 we should divide by 2. Divide 1.5 by 2.
Divide or multiply. Okay, you have to represent the distributed force with concentrated force, right? So I will replace that distributed force here with concentrated force of 1.5 kilonewton per meter multiplied by 2 meters. So the concentrated force is supposed to be 3 kilonewton. You get it, Safra?
Yes, sorry.
So that 3 kilonewton concentrated force will replace that distributed force of 1.5 kilonewton per meter. Okay. So now let's do the calculation of the Px, Py, and moment. Okay. Using sigma Fx equal to 0, what you have there?
Px equal to
Px equals 0, right? And then using sigma Fy equal to 0, what you will get?
By minus 3 minus 2.
By By minus 3 minus 2 is equal to 0. So By is equal to
5.
5 kilonewton, correct. And using sigma moment at P equal to 0, what you will get?
3 times 1.
3 kilonewton. Yep, correct, 1, because the location of the concentrated force is 1 meter from the edge. 3 kilonewton times 1 meter. What else?
Minus 2 times 2.
Minus plus, right?
Plus 2 times
Plus 2 kilonewton times 2 meter minus m equal to 0, right? Hello, Safra?
Yes, sir. Yes.
Yeah. So the moment is equal to 3 plus 4, right?
7.
Yeah, 7 kilonewton meter. So we have it. We have all the forces that in the in our case there. Okay. Now,
Excuse me, sir.
Yep.
I think we should multiply the 2 kilonewton by 4.
2 kilonewton by 4. What do you mean by? Sorry. Oh yeah, it's supposed to be 4, right? Correct. This one is supposed to be multiplied by 4. Correct. Yeah. So your moment is supposed to be 8 plus 3, so 11, right?
Yes.
11 kilonewton meter. Yes, this is it. So the moment we will have no Px, we will have By equal to 5 kilonewton going up, and we have a moment 11 kilonewton counterclockwise. Sorry, this one is minus m, right? Oh, so moment is I made a mistake. Sorry. This one is plus m, because all of those are counterclockwise, right? 3 kilonewton multiplied by 1, 2 kilonewton multiplied by 4 plus m, all of those are counterclockwise. So our moment is minus 11 kilonewton meter. So it's supposed to be clockwise moment. Okay, Saura?
Okay, sir.
So if we have to draw again, this is our final free body diagram. We have 2 kilonewton. Then we have a distributed force. Yeah. constant distributed force 1.5 kilonewton per meter, and at P there we have By 5 kilonewton, and we have a moment clockwise 11 kilonewton meter. So that's our final free body diagram. Now, as we discussed before, we will do two sections. Okay, the first section is here. The second section is here. Okay. For the first section, okay, for the first section, you will let's finish the first section. For the first section, the x is supposed to be between 0 to 2 meters, right, Safran?
Yes.
Okay. And the free body diagram that we have will be quite simple, like this: 2 kilonewton downwards. And what internal forces that we have there, Safran?
The shear force downward
Correct. V. What else?
and moment.
Moment clockwise, counterclockwise. Counterclockwise, because it will give a smiling face, right? And yet, this one, the distance is x, right? So using sigma Fy equal to 0, what you will get, Safran?
V equals 2.
V minus 2, right?
Yeah.
Equal to 0. Sorry, V plus 2 equal to 0.
V
Then V is equal to minus 2 kilonewton, right?
Yes.
Don't forget about the sign. And then using sigma moment at the left edge at A, right? Equal to 0, what you will get?
V times x.
V times x. So V is minus V is supposed to be going up, right? So 2 kilonewton times x. Okay. Then after that,
Minus moment.
minus moment. Are you sure minus moment? Just now, you want the positive, the moment positive clockwise or counterclockwise? Safran.
Positive for clockwise.
Clockwise, positive. So in that case, V multiplied by x is not positive because the value of V is negative, right?
Okay.
Yeah. So although V will give a clockwise moment, but the value of V itself is negative. So you have to put the negative there. Okay, Safran?
Yes. Yes.
Yeah. Minus 2 multiplied by x, and then minus m, right? Equal to 0 because moment is counterclockwise. Okay, so the value of moment there is supposed to be what?
2x.
Don't forget the sign. Minus 2x, right, Safran?
Oh yeah.
Don't forget the sign. Okay, moment is minus 2x. That's the first region. For the second region, for x between 2 meters until 4 meters, okay, do you want to use this cut or you want to use this cut, Safran? The left one or the right one? Both we can do it.
From the right one.
From the right one, okay. Let's draw it then. From the right one, we have By 5 kilonewton and clockwise 11 kilonewton meters. Okay. So what we have is like this. Okay. 5 kilonewtons upwards and clockwise moment 11 kilonewton meter. and distributed force 1.5 kilonewton per meter. Okay, at the cut there, what we will have, Savran?
Shear force upward.
Yeah, upwards, correct. Because it's positive clockwise, and then moment
Moment clockwise.
clockwise, right? And the distance is supposed to be what?
4 minus x.
4 minus x, correct. 4 meters minus x. So 4 minus x as our distance. Now this one will become a slightly more complicated. Okay, in order to find out for the phi, we will have to do sigma fy equal to 0. What we will have there, Safran?
V plus 5 equal to 0.
No, not just that. V plus 5. We have this one. Distributed force, remember.
3 kilonewton.
So you have to minus it with the distributed force, right?
Yes.
Yeah, the distributed force is what?
3.
Yeah, no, not 3. 1.5 kilonewton per meter. And the distance here is supposed to be 4 minus x, right?
Okay.
Yeah. So this is what you're supposed to do. Minus 1.5 kilonewton per meter multiplied by 4 minus x. Okay. That's the distributed. That's the concentrated force, which representing the distributed force, right? Hello, Safran?
Yes, sir.
Yeah, the length is 4 minus x. The distributed force is 1.5 kilonewton per meter. So the concentrated force, the resultant there is supposed to be 1.5 kilonewton per meter multiplied by 4 minus x, right? Equal to 0. So our phi is supposed to be equal to what? This one is minus 5. Okay. 10 plus 6. Then minus 1.5x, right? So phi is supposed to be equal to what? This 1, right? 1 minus 1.5x, right?
Yes.
That's our phi. Now, last one. It's slightly more complicated as well. If we want to find the moment, we have to use sigma moment. Okay. If we use sigma moment at P, okay, sigma moment at P here equal to 0, then what we will get in the sigma moment?
We have
starting with M, right? Clockwise, then what else?
V times 4 minus x.
Phi times 4 minus x. But remember our phi is this one, right?
Yeah.
So this one, M plus phi times 4 minus x. So phi, we replace phi with 1 minus 1.5x multiplied by 4 minus x. Yeah, that's one. And then how about the distributive force? Minus, right? Because it's supposed to be giving you a counterclockwise moment, right? Safran?
Yes, sir.
Yeah. So the distributed force, you have to multiply it with 1.5 kilonewton per meter multiplied by 4 minus x, and that one will become force, right? Safran?
Yes, sir.
And then how about the distance? The distance is supposed to be half this, right?
Yeah.
Correct, right? Because if we represent with the concentrated force, the concentrated force will become in the middle. So at 2 minus x per 2, right? So we have to multiply it with this one, 4 minus x per 2, right? Equal to 0. Do you get it, Safra?
Yes.
So 1.5 is the distributed force. We multiply it with the length. 4 minus x will become, that one will become the concentrated force. And the concentrated force, in order to become moment, you have to multiply it with the moment arm length. The moment arm length is half of this. So that's why the moment due to the distributed force become like that. Okay, Safran?
Okay, sir.
And now the equation. The equation is slightly more complicated, of course, here. It now become the quadratic. So the moment, it's supposed to be equal to, what's this? I will do it one by one. 4, this is from the first one, minus 4 minus 6x, and then minus 6 minus x multiple minus x, then the last one is plus 1.5x squared. That's from the first one, and then from the second one, it's supposed to be plus 1.5 multiplied by this 1.5 over 2 multiplied by 16 minus 4x minus 4x plus x squared equal to 0. Sorry, not equal to 0. It becomes slightly more complicated, right? So then we have minus 7x. Our moment here will become minus 4 plus 7x minus 1.5x squared. Okay. It will become a slightly more complicated. When we have a distributed force, it will become a slightly more complicated. 8. Now it becomes 6 plus 6 minus 3 minus 3 minus 6x plus 1.5, 0.75 x squared. 0.75 x squared. So our moment there will equal to minus 0.75 x squared plus x plus 2. So this is the equation for the moment. Okay, Zabra? Slightly more complicated. Yeah, slightly more complicated. Okay, now because we are running out of time, this is the calculation. Okay, but now how to draw it? Actually, I did it before. Okay, in the previous class, I already did it. Okay, so this is the graph after you finish the calculation. Okay, remember, based on our calculation, the phi is minus 2 kilonewton, and then for the first region is minus 2 kilonewton, and then for the second region is this one, 1 minus 1.5 x, right? Most likely there is a wrong calculation here, but the graph, so, oh yeah, right, 1 point, no, that one is not wrong. 1 minus 1.5x, so phi at the beginning at x equal to 2 meters, okay, at x equal to 2 meters, it's supposed to be minus 2, this one, because you have to put x equal to 2 there, and at the end x equal to 4, the phi is supposed to be minus 5, right? Because it's supposed to be minus 6 here. That's why it will become like this. Constant from the beginning, minus 2 until the starting point of the distributed force, and then linearly going downwards from minus 2 to minus 5 there. Then for the moment, it's slightly more difficult because the moment there, at the beginning, we have minus 2x. So at x equal to 0, we have 0 moment. And at x equal to 2, we have a minus 4 moment. So it's 0 to minus 4. Okay. Then after that, we will use this equation. Okay. The moment at x equal to 2 is supposed to be 4 plus 4 minus 3 minus 3 plus 2 plus 2, 1. Okay. Seems like the calculation may be a little bit wrong, but we can get the value of the moment at the beginning of the second region by putting the x equal to 2 here, okay, and get the value of it, and by putting x equal to 4 to get the end point of it. Okay, and this is our final graph for that particular point. Okay, so it's roughly right like that. That's the way to handle the distributed force. Any question here? It will be slightly more difficult than the concentrated force, of course, when we have a distributed force. Any question here? Anyone? Then this one is slightly more difficult as well because it's a continuous distributed force is linear going up. So it will be slightly more difficult to do so. I believe in your homework, okay, this one is your homework. Yeah, in your homework, I give as well a linear distributed force, so for you to exercise, okay, and the rest are the constant one, okay, and this one is concentrated one. Okay, anyone want to ask question here? Next week we will still continue on this, and we will discuss for the homework that I give you guys. This homework number 3 is from the previous exam. Okay. If there is no question, I think that's all for today. Okay. Thank you very much for listening, and see you guys next week. Don't forget to check for your homework in the EduNext. Okay. Please check your homework in the EduNext. Okay. That's all for today. Thank you very much. See you guys Thursday next week. Bye.
Yes, sir.
Thank you, sir.
Yes, sir.